Okay, let's go over AP number 28, which was 2006 AB3. This problem was a little different, but it wasn't too bad. But they did have a little twist to it, so let's go over it. So the graph of a function f is shown above. It consists of 6 line segments. Let g be the function given by g of x equals the definite integral from 0 to x of f of t dt. Well, as soon as we see that, just like in the other video, when we see that, the reader looks for this somewhere on your paper. They look for this statement, that the derivative of g gives back f of x, so that this is the graph of the derivative of g, which is f. That is very important in this problem. It's a great way to test what we could tell about the graph of g looking at the graph of its derivative. So let's begin. So part A says find g of 4. So when we substitute, we have the definite integral from 0 to 4 of f of t dt. And we have to find the total net area under the graph of f from 0 to 4. So when we do that, let's do that in another color. From 0 to 4, we've got this triangle and this trapezoid. So let's find the areas. Now 1 is below the x-axis, so the area of that triangle will be negative, but the trapezoid is above the x-axis, and that would be positive. The base of the triangle is 1, its height is 2, so its area would be 1/2 2 times 1, which is just 1. And the area of the trapezoid will always identify the parallel sides, which are the bases. So the base of this trapezoid is 1, 2, 3. The other base is 1, and its height is 2. So the area of this trapezoid would be 1/2 the height, which is 2, times 3 plus 1. So that would give us 4. So -1 plus 4, the answer to this is 3. Okay, let's look at part B. Now, I'm sorry, the derivative of g at 4. Well, the derivative of g of 4 is just, f of 4, because we have this statement here, just like in the other problem that we did. And f at 4 is 0, so that was an easy one. The second derivative of g at 4 would be the first derivative of f at 4 if we differentiate this again. So what we have to do here is we have to find the slope of the line. So we have to find the slope of this line at 4. Well, that's the slope of the line, because any point in between x equals 3 and x equals 5 would have the same derivative. So we have to find, well, we use the endpoint. So it's the difference of the x's, so that's 2 minus -2 over the difference, the difference of the y's, 2 minus -2 over the difference of the x's, which is 3 minus 5. And that would give us 4 over -2, and the answer is -2. So that takes care of those answers. All right. So one was to find the area under the graph of f. The other one was to differentiate and use f. And the second derivative required to get us the slope of the graph of f. All right, now let's look at part B. Part B says, does G have a relative maximum or minimum or neither at x equals 1? Justify your answer. So we only need to look at 1. Now, if we look at 1, notice that if we make a number line around 1, the graph of the derivative of g, which is f, is below the x-axis, so that makes the derivative of g negative. And to the right of 1, the graph of the derivative of g is above the x-axis. So immediately we could say that g has a relative minimum at x equals 1 because the derivative of g changes from negative to positive at x equals 1. And that would be enough. Or you could say because the graph of g changes from decreasing to increasing at x equals 1. All right, that takes care of part B. Part C is very, very different from what we're used to. Let's take a look at that. Okay, part C says that f is defined for all real numbers x, and it is periodic with a period length of 5. So if you go back to trig functions, when we say a graph has a period, its shape repeats in a certain interval. And this shape here repeats every 5 units, as we see to the left. The graph above shows 2 periods of f. Given that g of 5 is 2, find g of 10 and write an equation for the tangent line to the graph of g at x equals 108. So let's take it a step at a time. To find g of 5, and well, we know g of 5, but we want to find g of 10. Okay, so let's just do that. So I know that g of 5 is 2. I don't know what g of 10 is. So what we could do is we could set up a definite integral that would give us these values. And the way to do it is the following. We want to get g of 10. Oh, sorry. We want to get g of 10 minus g of 5. And the integral that would do that is the integral from 5 to 10 of the derivative of g. Okay, now this is really far-fetched, but if you think about it, when we integrate a derivative, we get back the function, so that gives us g. And with the first fundamental theorem of calculus, we substitute the upper limit first and then the lower limit. And that would be true. Okay, so we don't know what this is, but I know that this is 2. To get the answer to this is asking something else. It's really, if you recall, it is really the definite integral from 5 to 10 of f of t dt, right? Because we know that the derivative of g gives back f. So the derivative of g at t gives back f of t. So what this is asking, really, is to find the total net area from 5 to 10. Okay. Well, the total net area from 5 to 10, because this has a period of 5, would be the same as the total net area from 0 to 5. So I'm going to write this. Okay, so let's get the total net area from 0 to 5. All right, to get that, we have to get, okay, so I'm going to underline this. We have to get the area of this triangle and this triangle and this trapezoid. All right, so let's begin. Let's start with the trapezoid. And I think we did this no, actually, we got the area from 0 to 4. The area from 0 to 4 is already 3, right? From part A, we could do that. So we know that from 0 to 4, the answer was 3. So all we need to do is add the area from 4 to 5. And the area from 4 to 5 is this triangle down here, which would have negative area. But we see that its height is 2, its base is 1, So its area is also another -1. So this would give us -1. And when we add them, we get 2. So the answer to this integral is 2 equals blank minus 2. So the question mark is 4. So the answer is g of 10 equals 4. So that was a beautiful way to test the first fundamental theorem of calculus, as well as the first fundamental theorem of calculus part 2 and the geometrical interpretation of the definite integral. Now let's answer the next part. Find the equation of the tangent line at x equals 108. All right, now to get the equation of the tangent line, we need 2 pieces of information. We need the point of tangency. So we know that the point of tangency is 108 comma g of 108. And we also need the slope of the tangent line. And the slope of the tangent line is the derivative of g at 108. However, we have to find what this is equivalent to with a period of length 5. So let's think about this. Now, to get the derivative of g at 108, well, that is f of 108, right? Because we know that the derivative of g is equal to f of x. So this point, if we take 108 and divide it by 5, we get 2 and then 1 with a remainder of 3. So this would give us 21 complete cycles of the graph with a remainder of 3. So this is equal to f of, I believe it's equal to f of 3. So f of 3 here is just 3. If we look on the graph, f of 3 is, f of 3 is 2. That's the y value. So that would be the slope of the tangent line. Now, as far as what the value of g is at 108, we have to think very carefully of what this means. This is the definite integral of f of t dt from 0 to 108. But now we have to think of the complete cycles. So this one was where it was different, very different. So we know that the closest multiple of 5, closest to 108, is 105, correct? Because 21 times 5 is 105. So this is the definite integral from 0 to 105 of f of t dt, plus the definite integral from 105 to 108 of f of t dt. We have to find those areas, or at least what they're equivalent to. Well, we have to make them equivalent to one period. So as far as the periods are concerned, there are 21 periods from 0 to 105 of the definite integral from 0 to 5. So what we have to do is we have to find the total net area under f from 0 to 5 and multiply by 21. As far as this is concerned, this is really from 0 to 3 of f of t dt, which is really g of 3. So we have to find the total net area under f from 0 to 3. So, okay. So if we go through this, let's find the total net area. Well, let's try to do this as efficiently as possible. This triangle is identical to this triangle. So if we find the area of one such triangle and double it, that would take care of those two areas, but they're negated. So the area of this triangle, well, it has a height of 2 and a base of 1. So the area of such triangle would be 1/2 2 times 1, which is 1, but we double it, we get 2, but we negate it because we have 2 of them. So this is 21 times negative 2. Well, we'll do that later. So these 2 give us negative 2. Okay. Now, as far as the trapezoid is concerned, well, that the base is 3 and 1, and the height is 2, and I think we found that the area of that trapezoid is 1/2 of 2 times 1 plus 3, and that gives you 4, I believe. So the total net area of this region would be 4 minus 2, which gives us 2. But we have to multiply that 21 times. So that would give us 42. But the area from 0 to 3, well, again, this is negative 1. And now we have to take a look at this trapezoid. Okay, so that trapezoid has a base of 2, a base of 1. That's 2 plus 1, and 1/2 of 2. So that would give us just 3. So it would be negative 1 plus 3, which would give us a 2. So altogether, the area would equal 44. But we didn't write the equation of the tangent line. The equation of the tangent line, if we put it all together, would be, okay, let's see, y minus the y coordinate, which is 44, that took us a while to get, equals the slope, which we found to be 2, times x minus the x coordinate. So this was the first equation of a tangent line that I ever saw that took so much time to get. And that was only because we had to use a little bit of creativity and the fact that the curve was periodic. Okay, I hope that cleared up any questions you may have on this AP. Have a great day now. Bye.